Hi guys, today we're going to look at our learning target 12 notes and information on solutions, acids, and bases. For this assignment, what you're going to do is watch this video and then you're going to take Cornell notes following these objectives. So these objectives are going to become your cues. You're going to add notes in the notes section, and then don't forget to add a summary at the end when you have finished. So let's get started. These are our 8 learning objectives for this learning targets, and so we're going to describe, identify, calculate, compare, contrast, explain, calculate, and then again identify and write related to solutions, acids, and bases. So what is a solution? A solution is made up of a solute and a solvent. Those two things together create a solution. The solute does not have to be a solid. Solutes can be solids or liquids or gases, and the same thing with solvents. They can be solids, liquids, or gases. A solution, however, is going to be a solution that's in a similar state to either the solvent or the solute. So there are different types of solutions. Not all solutions involve a solid dissolved in a liquid, so that's kind of what I was explaining there. Air is dissolved, so like the air that we're breathing currently right now is oxygen dissolved in mostly nitrogen gas, so actually about 70% of the air we breathe is nitrogen. And so that oxygen is actually dissolved in that nitrogen gas. When you're drinking soda, you have CO2, so you have a gas dissolved in that liquid water. That should say H2O. Vinegar is acetic acid dissolved in water. Sugar syrup would be sugar dissolved in water, so any of those. A dental filling, this one is a fun one. It's a different kind of mixture that actually becomes a liquid when you mix these two things together, so mercury and silver. Brass is zinc dissolved in copper, and steel is carbon with iron mixed in, which adds that strength to it. So different types of solutions, they don't always have to be liquid-liquid or liquid-solid. So there are 3 other terms that are important to know when we talk about solutions: unsaturated, saturated, and supersaturated. So if we have an unsaturated solution, that means that I can add more solute and it will dissolve. If I have a saturated solution, no more solute will dissolve in that solution. So if I added a little bit more, it would become supersaturated. So a supersaturated situation is when crystals are growing, or like you put too much sugar in like your tea or something and it sits at the bottom of your cup. Okay, so unsaturated, I can keep adding more solute to my solution and it will keep dissolving. Saturated is like a very, very, very finite point where no more solute can dissolve if I added it to the solution. Supersaturated then is when I have more solute than the solvent can dissolve. So there are some ways we can affect these saturation points, and we can also graph what these look like and represent that graphically. So solubility is the maximum amount that can dissolve in 100 grams of solvent at a certain temperature. So temperature is really important when we talk about solubility. Think about hot tea versus cold tea. You can dissolve a lot more sugar in hot tea than you can cold tea. And that's because temperature, as we increase temperature, solubility usually increases. There are a few cases where that isn't true, but usually as we increase temperature, see if we go to the right here, our solubility is going to increase. So if you look at this graph, we have a line. The line is the saturation point based on temperature. So let's say we were at this middle point temperature and I go up to the line. This would be the amount of grams that would dissolve in that solution at that temperature. If I added any more, it would become supersaturated and you would have those crystals at the bottom. Or if I didn't add that up to the saturation points, I would have an unsaturated solution. So again, supersaturated, saturated, unsaturated. So here's an example of a solubility graph of actual chemicals. So we have sodium nitrate, calcium chloride, lead nitrate, and sodium chloride. So sodium chloride is one we know. This is table salt. Look at its line. It's fairly horizontal. And that's because temperature doesn't really affect how NaCl dissolves as much as like KNO3. So you see how KNO3 has a super steep slope on this line? And that means that as you increase temperature, dramatically changes the amount that can dissolve in that amount of solution. So how can we use this graph? We can use this graph or these charts to tell us how much we could add to a solution to have it at its saturation point. So how much CaCl2 can dissolve in 100 grams of water at 10 degrees Celsius? So I'm going to look at my 10 degrees Celsius down here, and I'm going to try and find CaCl2. So I'm going to go up, 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 up. Cool. So CaCl2 crosses the 10 degree mark at like maybe 64 grams. So 64 grams would be the amount of CaCl2 that could dissolve at 10 degrees Celsius. The other way you can use this is, what temperature would 40 grams of NaCl dissolve in 100 grams of H2O? So if I have 40 grams, I go all the way over on 40 until I hit that light blue line, which looks like right about 90 degrees Celsius. So you can use this to find the temperature or the amount of solute that you can add based on that temperature. How to increase solubility. So there are three main ways you can increase solubility. The main one we've been talking about is temperature. If I increase temperature, generally the solubility increases. You can see that there is, oh, it doesn't have it on this one. There's one that's not the case. Oh, here we go, yeah. Cesium sulfate is one that actually temperature doesn't increase the solubility, it actually decreases it here, and that's kind of a weird one that we don't see very often. The other is increasing surface area. So if you were to add like a cube of sugar to your tea versus granulated sugar, it's going to take longer, and or it might not all dissolve in that cube form because the surface area is smaller. If I break up that cube of sugar into granules of sugar, the surface area increases and the ability for it to dissolve increases. And same thing with stirring. Stirring is really increasing temperature and surface area very slightly, but that's what helps it increase solubility. So three different things that can help us increase how much we can dissolve in a solution. All right, so how can we measure the amount of solute mathematically? So in chemistry, we always look at things qualitatively and quantitatively. So qualitatively, visually, we can see that there are crystals on the bottom and it's not dissolved. Quantitatively, we can measure that using this term of molarity. So I really like this picture of like 2 moles per liter. So there's 2 moles in a little beaker down here. But really, molarity is a way to describe the concentration of a solution. Concentration meaning how much solute do I have in that solution. So molarity is a big capital M that we use for our unit, and it's equal to the moles of solute divided by the liters of solution. When we're calculating molarity, we have to use liters for our calculations. So often you'll be measuring or given milliliters, but you need to use liters when doing your molarity calculations. And so you can use the unit of M or moles per liter when describing molarity. So let's go ahead and try one of these. If you have 5 moles of NaOH and you dissolve it in 0.5 liters of water, what is the molarity? So we have 5 moles, we have half a liter, and we're looking for molarity. Again, molarity is moles per liter. So we're going to do 5 divided by 0.5, which is going to be 10. So in this case, I end up with 10 moles per liter for my molarity. I can use a big capital M for my unit, or I can say moles per liter. Either of those are correct ways to represent a molarity. And so this is a quantitative measure of how much solute there is per amount of solvent in a solution. So what scientists can then do is dilute solutions. So oftentimes when scientists purchase solutions and things to use in the lab, they're very, very concentrated. So for example, if we buy hydrochloric acid, it's going to be at 18 molar. 18 molar hydrochloric acid will eat through your skin. It will dissolve some materials. It's very, very corrosive and dangerous. We don't buy it because of that. We buy it because we can take that 18 molar 1 liter container and turn that into a ton of hydrochloric acid at 0.1 molar that you guys can use. So concentrated solutions often need to be diluted. Think about this in like if you were to drink like Kool-Aid and you didn't add enough water to it, it would be like really tart and not very good. So you could dilute that and make it more kind of palatable to your taste buds. So it's the process of reducing the concentration of a solution by adding more solvent, okay? So the way that we can do this and figure out what our molarity is or how much water to add is by doing M1V1 is equal to M2V2. M is our molarity, and V is our volume. So similar to our gas laws we were looking at, our 1s are our initial situation. So that's your stock amount, and then your M2V2 is what your goal is. What are you trying to make? What type of concentration are you trying to get? So here's a real world example. Right now with COVID, everyone's cleaning and sanitizing. There is a certain concentration, I think it's 70% alcohol, that is needed to kill bacteria and viruses. So when you take 100% isopropyl alcohol or ethanol or whatever, you need to dilute that down to that 70% in order to kill the bacteria effectively, but also not burn your hands. If you were to use 100% alcohol, our hands would literally just peel and be really, really, really dry. So diluting that alcohol solution helps us so it's useful but not damaging to our skins. It still dries us out, but that's a whole other story. So let's take a look at calculating an example of this. If I dilute 250 milliliters of 0.1 molar lithium acetate solution to a volume of 750 milliliters, what will the concentration be? So notice I'm adding 500 milliliters of water, and I'm looking for what the concentration of that solution is going to be. So my first molarity is 0.1. My first volume, remember I need to change into liters, and then I'm looking for my second molarity after I change the volume to 750 liters, or milliliters. Notice that the wording on these questions is tricky. So I'm changing the solution to be 750 milliliters. I'm not adding 750 milliliters. If I said adding 750 milliliters, this would end up being 1 liter because I would be adding it to what I already had. So pay attention to how the questions are worded. In this case, I'm just telling you what that final volume is. So you're plugging this into your M1V1 equals M2V2. You can combine your left side of the equation here to get 0.025. You then can divide by 0.75 to get 0.033 molar. And so we use the term molar when we're talking about this unit. So we would change our solution, and it should make sense that this number is smaller than the molarity we started with because I added more water. I diluted my solution, so it should be less concentrated. And remember, molarity is a measure of that concentration. Okay, let's pause there, and I'm going to make a second video for acids and bases. Let's go back up to the beginning and look at our objectives. So we described the factors about that affect how fast and how much a substance is dissolved. We identified saturated, unsaturated, and supersaturated solutions using a solubility chart. And we compared we calculated the molarity of a solution using moles per liter. So we've looked at these 3 learning objectives. In the next video, we're going to look at the next ones related to acids and bases.